하겠습니다. Okay, welcome to the makeup class. So let's continue to cover the cache memory. So I think in the morning we briefly covered how cache is organized. It actually have multiple sets, and each set actually has one or more blocks in it, right? So that's basically how we organize the cache. And there are three parameters that actually characterize cache design. So we actually have like number of sets, S, and associativity, E. How many blocks are there in a single set. Finally, B, which is how many bytes are there in the single block, right? So these like three parameters actually specify a cache design. So we went over two cache design, direct map cache, where E equals 1, right? There's only one block in each set. And second one was two-way, n-way, like a set associative cache, where there are two or more blocks in a single set. So that's what we covered in the morning. And let's continue. Let's take a look at some more realistic cache design. So this one is like Intel's Core i7 cache hierarchy. This design is actually like several generations behind. I mean, it's like several years ago. It's based on like Haswell, but pretty much the cache design is more or less the same in today's like i7 cache design. So in this design we have level 1 instruction and data cache. As you know, there are two separate pieces of like caches. The first one is instruction cache or iCache. The second one is data cache. So we actually have two separate like physical entity for instruction and data caches. And level 2 cache is this one is like a unified cache in a sense that now we actually have both. This cache actually has like a unified design to hold both instruction code and data, program data, in the same cache. Finally, there's like a L3 unified cache which also holds both instruction and data, but this is shared by all the cores on your chip, right? So that's basically a hierarchy of cache design. So L1 cache, it actually has like a 32 kilobyte in size, an 8-way set associative cache, and it takes like 4 cycles to access. It actually takes like multiple cycles to access the cache. But it's because this process actually runs at very high clock frequency. It actually runs like 3 to 4 gigahertz range, right? So it's actually the cache access itself is pipelined. So it actually takes like 4 cycles to finish like a single access. But there are like multiple accesses are actually pipelined. So there are like multiple instruction fetch and data fetch actually going on at the same time. So that actually takes 4 cycles. In L2 unified cache, it's like a 256 kilobyte in size, also like 8-way set associative cache. And access time is about like 10 cycles, 10 CPU cycles. And L3 unified cache is like huge, like 8 megabyte big like cache, 16-way set associative cache. And access time takes like a 40 to like 75 like cycles. But in like this, it's because, as I said, this one takes like many cycles because it's running at a very high clock frequency. But in like a mobile or embedded processor, which is running at a much lower clock frequency, it's not uncommon to have just like a single like a cycle access for cache. I mean, if you're actually running like a 1 gigahertz or like lower frequency, then it only takes like a 1 clock cycle to finish accessing the cache. So in typical like embedded processor, it's like it takes like 1 through like 3 cycles. In embedded or mobile processor, which is running at much lower frequency. But in this case, this one, as I said, this one is very high frequency deeply pipeline design. So it actually takes 4 cycles. 한번 try. So let's think about what's the cache performance metric. Of course, what is good cache, right? So in order to evaluate that, 카메라가 저를 트랙을 못 해가지고. So what is a good cache? You actually have to measure the performance of cache in some way, and one of the most like important measure is miss rate, right? If you actually design cache well, you actually have to achieve very high hit rate. So whenever you actually try to access the cache, you want to find, it'd be great if you can find, those blocks as many times as possible, right? So that's where you can, miss rate or hit rate. So the miss rate is defined as 죽었나 보다. Rest in peace. 나중에 한번 고쳐봐요. Okay, so miss rate is defined as fraction of memory references not found in the cache, right? It's like the numerator is the misses, how many misses, cache misses you have, and the denominator is accesses, right? So it's like you divide the misses divided by total number of accesses, and this one is like a 1 minus hit rate. Okay, it's kind of 1 minus hit rate is miss rate, 1 minus miss rate is hit rate, right? So, and typical number in percentage. So L1, like a cache miss rate, is somewhere between 3 to 10%. Is kind of reasonable, like typical like numbers. Actually, the hit rate is pretty high, right? Because that means the cache hit rate is somewhere between, like a 90% to 97%, right? Which in turn means that if you access the cache 100 times, 90 times it will hit, right? That's what it means by this cache miss rate. But it can be quite small for L2. This is actually not. Sorry, this is not really true. Generally, L2 cache miss rate is generally higher than L1. So what's the reason? Why this L2 miss rate can be higher than L1? So the way cache works is that you first check out the L1 cache, right? And then your block is not there. You have a cache miss. Then actually you go to L2, right? And you check the L2. If it's not there, you go to L3, right? That means all these accesses with high locality is already filtered by the level 1 cache, right? Or level 1 or higher cache. So if you actually access goes to L2, that means you already those highly accesses with high locality is already filtered by this like a L1 cache. So it actually L2 cache access is looks much more random than the L1, right? So generally speaking, L2 cache actually has higher cache miss rate in general. And the second measure is hit time. So hit time is how much time it takes to deliver a cache line to the processor. So it also includes the time to determine whether the block or line is in the cache. As I said, line and block I use interchangeably, right? Line and block the same thing. So typical numbers, hit time in the previous design in Haswell processor, it took 4 cycles for L1, and 10 clock cycles for L2, maybe 40 cycles to 75 cycles for L3, and so on, right? This kind of typical number. Of course, if you actually if your processor is running at a lower clock rate, then the cycle count will decrease, right? Because if you actually run at 1 gigahertz, 1 cycle is 4 times longer than a 4 gigahertz processor, right? So that's a second measure, hit time. And the third measure is miss penalty. So miss penalty means, let's say, let's say you have cache miss. Then how long it's going to take to fill the cache block into the cache? That's called miss penalty, right? So So we have a pipeline here, process pipeline. We have a level 1 cache, and we have level 2 cache here, L2, right? So let's say pipeline issue a memory request, like load instruction or store instruction or instruction fetch. Then, if it hits, then actually it returns the requested word into the pipeline, right? That time is like a hit time, right? Because it's a hit time because how many cycles it takes for starting a request and then getting a response, right? This is hit time. And if you actually have cache miss, basically cache miss means how many times you missing the cache for a given access. Right? So what's the probability of having a cache miss for a given request? So if you have a cache miss, now you actually go to L2, right? So some may somewhere, if it's in L2, you actually get the block from L2. If it's not there, you go further down into the hierarchy, go to the main memory, and then if it's there, then you actually get it from the main memory. If it's not there, you actually even go to the disk, right? And you get the data from the disk, and then it comes back eventually to the pipeline. Then that is called miss penalty. How many cycles is going to take once you actually have cache miss here, right? That's miss penalty. So it is defined as additional time required because of cache miss. So typically, 550 to 200 cycles for main memory. So if you have to go to the main memory, you have to access DRAM, and DRAM access time is somewhere between like 50 to 200 like CPU clock cycles. Okay. So if you remember, like last time, I actually showed you a trend figure. So there was like a figure. X-axis was year, and Y-axis was the access time for like different devices, right? Like a disk, DRAM, SRAM, and so on, right? And if you remember, the DRAM's trend curve was something like this. It's actually decreasing, but it's very like slowly. I mean, it's relatively very stagnant, right? It's very flat. But CPU cycle time was decreasing much faster, like this. I mean, like this, right? So there was like an increasing gap between the DRAM access time and CPU cycle time. So that's the reason why this trend is increasing. But today, the CPU frequency scaling also is kind of stagnating. I mean, it's kind of stagnant, right? So it's still it looks like this. So now this gap is relatively relatively constant compared to the previous years. But still, I mean, there's a huge gap between these two CPU cycle time and memory access time. So it takes like 50 to 200 cycles to access a data from main memory. So let's think about these numbers. So there's huge difference between hit and miss. Could be like a 100x difference if just L1 and main memory. Let's say our cache, for example, let's say we have pipeline again, pipe, and L1 cache, which is backed by main memory. Okay, so yes, let's say, but would you believe this 99% hit is twice as good as 97%? If you hear that one cache actually has 99% hit rate, the other cache actually has 97, then you think, oh, what's the difference? It's just 2% difference. What's the deal? You may think in that way, but that's actually not true. It actually has huge difference. 99% hit rate and 97% hit rate actually has 2x, as much as 2x difference in terms of average memory access time. Okay, let me explain why. So let's consider that, let's say cache hit time is just one cycle, meaning that if you actually have cache hit, the data actually comes immediately in the next cycle. Let's say it takes only one cycle, which is not uncommon in embedded and mobile processor. And secondly, let's assume miss penalty is 100 cycle. As I said, if you actually have to go to the off-chip DRAM, it takes at least 50 cycles and up to 200 CPU cycles, right? Then what is the average memory access time in both cases? I mean, the first case is hit rate is 97%. In second case, the hit rate is 99%. What will be the average memory access time? Right? Expected value of memory access time in both cases. In the first case, the average access time can be calculated in the following way. If you have 97% hits, then your average access time is one cycle plus 0.03. This is a miss rate, right? Because 3% of requests actually will go to the main memory, which actually takes 100 cycle, right? But in case of a hit, now you only have one cycle, right? So if you actually calculate the weighted sum, then the average memory access time in this case will be four cycles, right? But what if actually you have 1% miss rate or 99% hit? Then only 1% of requests will go to the slow off-chip memory, right? It will take 100 cycles, but otherwise it only takes one cycle. Sorry. So it will be the the access time, average memory access time will be 2 cycles, right? Then maybe if you're like careful, like if you have sharp eyes, then you may ask question, why shouldn't there be like 0.97 factor here, like here, and 0.99 factor here? If you really want to calculate the weighted sum, like 99% takes like one cycle, 1% take like 100 cycles, then shouldn't be like 0.99 and 0.97 factor in the first term? That's actually a valid question, but the truth is, before you actually have to go to the off chip, you have to first check whether the data block is currently in the cache or not. That actually takes 1 cycle, right? So in other words, regardless of whether the data is currently in the cache or not, you still have to look up the cache anyway, right? Because only after you find, oh, there's like the data is not there, you can actually go to the go off chip, right? So this is like a 1 cycle like cost will be paid regardless of whether you have cache hit or miss, right? That's the reason why we don't really have like a 0.97 or 0.99 here, right? Okay, so the takeaway here is that, so that's the reason why miss rate is more, relevant. I mean, more like a realistic like a measure than hit rate, because if you think about a hit rate, it's only like a 2% difference, right? But in case of a miss rate, it's like a 3x difference, right? 1%, 3% is like a 3x difference, right? So miss rate actually reflects this impact, performance impact, more, realistically, right? All right. So the next topic is how we can how we can write so-called cache-friendly code. Okay, because of cache, even if your program actually does the same thing, version A, version B, they actually do the exactly same thing, but their performance can be widely different because of the caching effect, right? Some of the program actually has, better, like exploiting this cache better, and other programs may, exploit this cache poorly, so that, even though they actually do relatively more or less the same thing, their performance can vary widely, right? So, our strategy is make common case go fast. The common case is, let's say we have a loop, like a multiple, like a nested loop, like a for I something inside here, for j something, and inside here we have for k something, and this inner body, this like a the body of the innermost loop will be the most frequently executed part of the code, right? So we better actually optimize this part than like this part or this part, right? So that's what I mean by make common case go fast. And we also want to minimize the cache misses in the innermost loop, right? Because so in doing so, the repeated references to a variable are good, right? Because if you access the same variable again and again and again in the body of the innermost loop, then that's good, because you can actually exploit like a spatial locality in the cache, temporal locality in the cache. And stride 1 reference patterns are good. So stride 1 means that, let's say you access like I of 0, A of 0. In the next iteration, you execute A of 1. And then in the next iteration, you execute A of 2. This one is stride 1 pattern, right? Because, in the following iteration, you basically you read like adjacent like word, right? So that's basically stride means the distance between the 2 consecutive accesses. So in this case, this stride, the difference is just 1, right? Stride is 1. The difference between 2, adjacent memory accesses. So stride 1 reference patterns are good. Stride 2 is also fine. Stride 2 is maybe 0, 2, 4, 6, 8. It's not as good as 1, but still there are like ample like a spatial locality, so it's kind of okay. But if you actually have like a random access pattern, or very like a long like a strided accesses, then probably it's not very good. Okay. So key idea, you want to actually apply these like ideas to actually optimize this like code. So let me give you an example how you can optimize loops for cache performance. So let's think about more concrete example, how we can optimize a program for, best utilize the caches. And let's think about, first of all, let's think about memory mountain. So what is memory mountain? So here is like a, let me define read throughput first. So let's say you actually make a lot of like memory references. Let's say you access the memory, like a lot of like load and store instructions. But the read throughput is basically number of bytes read from memory per second. So its measure is unit is a megabyte per second. So basically, let's say you execute your loop and it's finished in 1 second. And the total amount of memory reference your program generate was like, let's say 300 megabyte. Then the memory like a read throughput will be 300 megabyte per second, right? Because you generated like 300 like a megabyte. You actually read like a 300 megabyte of data in like 1 second. So it's like a 300 megabyte per second, right? It's kind of obvious thing. And the memory mountain is, basically we measure like a read throughput as a function of spatial and temporal locality. And, this is actually a compact way to characterize systems performance. So let me show you, this is an example of like a memory mountain. So in the 2 slides later, in slide 24. So let me, before you explain this figure, let me explain how we generate these memory mountains. So in this memory mountain actually has 2 parameters, x and y. So x and y is like a stride and size of array, and y-axis is a read throughput. The higher is better. A higher number is actually means better performance. So in order to generate like this memory mountain figure, we actually use this test program. Okay, so this test program is a very simple C program with like array called data here. So we actually have like array. Like a global like array is defined here, and this is a test function which takes 2 parameter as input. The first one is elements, like a number of elements, how many elements this array has, right? So this first variable actually controls the size of the array, right? How much, or like memory footprint. So this is called memory footprint because how much like memory space your program actually access, right? So this is called a memory footprint. Sorry for the poor writing. Footprint. So the like first like parameter actually controls memory footprint. How large is the memory space you're accessing, right? So that's the first parameter. And the second parameter is stride. Stride is, again, as I said, what's the difference between these adjacent memory accesses, right? We actually control the second thing with the second parameter called stride. And this is the body of the loop, main body. So now we actually have like a for loop with like within the limit. So limit is kind of the maximum, region you can actually access. So so in this case, there are like 4 lines in it. The first one is, accumulating like a data array with stride 1. This one is like a stride 1, right? The first one is like a stride 1, this one, because in the first iteration you access data 0. In second iteration you access data 1. In third iteration data 2, data 3, and so on. So this line actually has a stride of 1. It's very like local. Stride 1 access pattern, which is very well performing. And the second one is data I plus stride. So stride is parameter here. So in this case, you also access, this I plus some like a data from in a constant distance, right? Constant distance from the current value. So so you access like this like a constant stride value. Also plus like SX2. SX2 is like a stride times 2. SX3 is a stride plus 3, and this one is stride plus 4. So each of these things actually access the memory in like a different stride. Right, so so that's basically how you access this program. So because you add like SX plus 4, so in this case, if you have a stride something like this, these four thing actually access, like you divide this like a let's say this is stride. Let's say you have stride. This is a stride. So stride is parameter. Then these four axes falling in like a 0.0, point like 1/4, point like half, and 3/4, right? So this one has got 0, maybe like a 25%, point, 50%, and 75%, right? And this is a stride, right? This is a stride. So we actually access, this like every iteration, the index actually increases by stride sx times 4, right? Stride times 4, and this one actually is like a stride times 2, stride times 3, and then in the next iteration you start again here, like a stride times 4, right? Here, 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 and so on, right? So depending on the value of the stride, your like this like a shaded box actually have like a wider, gap or like a narrower gap depending on the value of the stride. So that's pretty much like what this loop does. And actually we measure the read throughput using this program, and this actually shows a memory mountain. So if you see here, not surprisingly, if you actually have like a smaller stride means that in the previous figure, these four axes will be very densely packed, right? If you have like a smaller stride, then this one will become very close to each other, right? So if a stride, for example, if a stride is 1, then it will be like adjacent, right? It will be like, they back to back. Axes will be back to back. It's very local. But if you actually have like a large like a stride value, then there will be like some like gaps will be there. Okay. Secondly, if you actually have size, that's basically size of the array, size of the memory footprint, how much memory space you access. Of course, if you actually access like a larger memory, then probably you actually have poor locality, because now this is actually if you have access like a large memory size, then actually it doesn't fit in the cache, right? So if you actually have like a small footprint, they will actually fit in the cache. But if you actually have a large memory footprint, then it won't fit in the cache, right? So if you see here, so first of all, if you see this like memory mountains, of course, as you go in this direction, the performance will be better, right? Because now we actually have a small memory footprint, so the small memory footprint will fit in the cache. And if you actually have like a small stride value, then actually the memory will be more like, actually has like a better spatial locality because they are close to each other, right? So this one actually has the highest point. And there's several things to note. The first one is, this one is called regions of temporal locality, right? So let's think about, this size factor. Let's say we fix this stride and we only just increase the size, right? So if you see here, at this point, performance will be the best, right? Because it's a very small array, right? It's a very small array, so entire array will fit in the cache. Then, basically almost like all memory accesses will cause cache hit, right? So this will be like a lot of, this will be performed very well. But if you actually still increase the cache, the array size, then eventually this cache, the array will not fit in the cache, L1 cache, right? So there's like a very dramatic like a performance drop once your memory size becomes larger than the cache size. Then now this like array now will fit in the L2 cache, level 2 cache, right? So there will be some like a ridge here, like some, like a plateau. As long as you have some plateau, as long as your memory size, array size fits in the level 2 cache. And of course, if you keep increasing the memory footprint, eventually it won't fit in the L2 either, and now it's going to fit in like L3 cache, level 3 cache. And there will be also like a plateau here. And then eventually, if your memory, this like memory footprint is larger than L3 cache size, then it won't fit in the cache, and you go off chip. Right? That's actually like reach of temporal locality. So there will be some like a discontinuity here, like this, depending on whether your actually array actually fits in L1 cache, L2 cache, or L3 cache, and so on. Right? And the second thing to note is that this one is like a slope of spatial locality. Okay, this one. if you see like this pattern, like this, then what this one shows is that if you increase the stride, let's say you increase the stride, then the distance between the two adjacent memory accesses will increase, right? So once you actually fetch the entire block, there are only like a few hits. If you actually have like a large, like a wider, the more like a wider gap between the two adjacent memory accesses. So if you increase the like a stride, then it actually shows a poor temporal locality. Because if you have like a very dense like a stride one axis, then basically you have very good spatial locality. But if you actually increase the stride, then now this like a spatial locality will be degraded, right? So that's actually is shown by this like performance degradation as you increase this like a stride, right? And finally, I don't really talk much about this prefetching, but if you see here, there's a relatively constant performance region, even though you actually increase the size of the array. Then what happens here is that the process actually does aggressive prefetching. So prefetching is I'm not going to go over prefetching in this course, but there is technique that you actually fetch the block even before it's actually requested. That's called prefetching. So prefetching is, let's say you actually have very like a regular memory access pattern, like A of 1, A of 2, A of 4, A of 6, A of 8, and so on. Then the processor is actually smart enough to infer that the next request will fall on A of 10, right? So it basically tracks the history of memory request, and then if it finds a certain pattern, then actually it requests that data even before the instruction actually requested. So that technique is called prefetching, and this one is this performance is still maintained even if you actually have a larger array because of the aggressive prefetching. But of course, prefetching is kind of a speculative technique. It's kind of prediction, right? So it will be good only when it actually is correct, right? But if it's incorrect, it's kind of waste. So prefetching, does not always provide like performance benefit. Sometimes, if a prediction was wrong, then it only generates like a waste in the memory traffic, right? So sometimes it helps, sometimes it doesn't, depending on the situation. But in this case, this one actually helps because we achieved about the same like read throughput regardless of the size of the cache, size of the array, right? Okay, so this is about the memory mount. By the way, is there any questions about what I covered today so far? 여기요? 반대로? 저쪽 방향? 매우 작아질 때? 이 사이즈가 여기보다 더 작아질 때? 아니, 떨어지는 거 아니에요. 떨어지는 게 아니고, 네, 이게 사실은 그림이 좀 애매하게 되어 있는데, 떨어지는 거는 아니고요. 이게 사실은 떨어질 수가 없죠. 그러니까 이게 그러니까 이렇게 설명하면 될 것 같아요. 떨어지지는 않고요. 떨어지지는 않는데 이런 경우는 있을 수 있어요. 이게 뭐냐면은 만약에 어레이 사이즈가 너무 작으면은 프로그램이 너무 빨리 끝나. 그래서 스테디 스테이트에 들어가기 전에 그냥 예를 들면은 앞에 처음에 프로그램을 시작하는 오버헤드가 상대적으로 이게 어몰타이즈가 안 돼가지고 좀 떨어지게 보이는 경우는 있을 수 있는데 이게 스테디 스테이트에서는 이게 더 나쁠 수는 없어요. 왜냐하면 더 작을수록 더 메모리의 핏이 더 잘 되거든요. 캐시 안에. 그래서 이게 실제로 떨어지지는 않아요. 근데 만약 떨어진다고 하면은 아까 얘기한 대로 처음에 프로그램을 시작할 때 이 루프를 도는 게 아니라 전체적으로 뭔가 프로그램을 실행하는 데 있어서 드는 컨스턴트 코스트가 있는데 그거에 비해서 이게 돌아가는 부분이 너무 짧은 거죠. 돌아가는 프로그램 루프의 부분이 너무 짧아서 그래서 뭔가 그것 때문에 좀 이게 전체적으로 이 리드 트루풋이 많이 떨어져 보이는 것처럼 보일 수는 있지만 이 루프에 있는 부분만 만약에 떼어놓고 생각하면 떨어질 수는 없어요. 예. Any other questions? Okay. So the next two things are about how we can optimize the like a program. In this case, a loop. We can take a look at like a nested loops. How we can optimize the performance of a loop, exploiting like a spatial and temporal locality. Okay. So the first the technique is about how we can improve the spatial locality of your program. Okay. So let's take a look what we can do for that. So here's a simple like a matrix multiply example. This one is like a nested loop with ijk. So this one is very simple, right? Because this one actually initializes the value of sum here, and then now we calculate the innermost loop to add the sum up, and then finally we write the value to the C of ij. Right? If you actually draw it, it'll look like this. So we have like a array A here, and we have array B here, and we have array C here, right? Then if you want to calculate the value of like a specific like a point like this, then you actually have to what you have to do? You have to calculate like a sum of product for this thing, right? That's how we calculate the value here. 우리 이렇게 이 로우하고 컬럼의 서머 프로덕트를 구해야지 이게 얘의 값을 구할 수 있죠. 요 포인트에. 그죠? That's matrix multiply. So like this, and we do this for all of the points here, like C, right? C of like I and J, right? So we actually have like three like a two-dimensional array. So here, we multiply n by n matrices, and each matrix element has like double type, like 8 bytes, the double precision floating point number. So how many total operations do we have? The order of n cube, right? Because we have like a triple like a nested loop, ij and k, each of which actually run by like n times. And then we actually calculate in the loop body, we calculate multiply and add here. Right? So the total number of operation will be n, somewhere like n cube, right? Proportional to n cube, right? And we do like n reads per like source element, because for each like a source element, we read like n times, right? Because to calculate the entire like row here, we actually have to read this thing like n times, right? And then we actually read like this one, this one, this one, this one, and so on, right? So for each like a source element, this one will be read n times, right? To calculate this entire like row of data in the destination. In order to actually calculate the entire row of data in C, you actually have to read like these elements like n times, like this, right? So that's the reason why each like a source element here, this one and this one, they all will be read like n times, right? And n values are summed over per destination, because in order to calculate this single value in the destination, you have to basically add up, all of these like a sum of products. You have to calculate the sum of products, and with like n like partial like products, right? Because you calculate like this. So n values are summed over, but maybe you can actually hold this like a sum variable in the register. So it may not necessarily causing like memory access, except that only at the last time you actually have to write the value into the memory, array C. So how we can optimize this program for cache? This is our baseline. So this is our baseline implementation of a matrix multiply. And let's make some few assumptions. The first one is block size is 32 byte. So this 32 byte is big enough for like 4 double variables, like 4 double value, because in double precision each number takes like 8 bytes, so it's like a 4 like a doubles. And assume like matrix dimension n is very large. That's kind of assumption. N is very. We actually do like a matrix multiply for the big like matrix. N is very large, so approximate n over 1 as 0. Cache is not big enough to hold like multiple rows. So cache is relatively tiny compared to the size of matrix. That's kind of assumption. Let's make that assumption. Which is not uncommon. I mean, our matrix is really big. Compared to that, cache is is tiny. I mean, that's kind of not uncommon. It's a pretty common situation. So here's analysis method. You actually see look at the access pattern of the innermost loop. So what will be the access pattern in the innermost loop over like while executing the loop? That's kind of our analysis. So here we actually review the layout of a C array in memory. So if you have like C array, the C array is allocated in row major order, right? In your memory space, let's say you have like a linear memory space, then let's say you have array A here. So array A, 0, 0 is placed here. Then what will be the next element? 1, 0 or 0, 1? 0, 1, right? So that's what I mean by row major order, because row is actually, you actually, all the data in a row comes first, and then you move on to the next row, and then you basically, place all this data in the columns, and so on. So this one is followed by A01, and so on. And then after you go through all of these n elements, now you go to A10, like this. Okay. So in this case, let's think about this simple like simple like a loop, which actually accumulate the array elements of 0, I. Okay. So what will be the access pattern here? What will be the memory access pattern for this thing? It will be very consecutive, right? A of 0, 0, A of 0, 1, A of 0, 2, A of 0, 3. So it will be, it's so-called a stride 1, right? Because, it reads the adjacent like a word, integer. It's not integer, it's actually like a double. This is the assumption. So if like a block size is larger than this element size, then we can actually exploit spatial locality. So in the previous slide, we assume the cache block size is 32 bytes, and then each element only takes like 8 bytes, right? So how many doubles you can pack? Like 4. So the access pattern will look like this. The first access will cause cache miss, right? And then either actually fetch the entire block, the 32 byte block, into the cache. And the next 3 requests will actually hit in the cache, right? Because first request actually generate a cache miss, and it's followed by 3 hits in the cache, right? Because the single block actually contains 4 doubles. In the next access, it'll cause another cache miss, right? So in the entire block will come into the cache. And it will be followed by 3 cache hits, right? Because now, entire block is fetched. So now the first one actually caused cache miss, but next 3 will cause cache hits, right? So what will be the steady state behavior? What will be the cache miss rate? In this 25%, 25%, right? So that's cache miss rate for that specific access. So if you generalize it, if you generalize the pattern, the miss rate will be, in this access pattern, the miss rate will be size of the array element divided by B. B is block size. So in the previous example, the size of this array element was 8, like 8 byte, right? And then block size was 32. So the miss rate was 0.25 in this example. But this is kind of more general form. So the if you actually have like a stride 1 access pattern, stride 1, then the cache miss rate will be, for this like access, will be, size of the element divided by cache block size, right? So let's think about, the other case, stepping through rows in one column. So now in this example, we access like this, right? But in this example, we now access like that, like this. And n is very large. N is huge value. Okay? Then what will be the cache miss rate here? So let's think about the access pattern. In the first access, we read A00, right? But it actually, because of cache miss, now we actually read like 4 doubles together, right? Like this. 4 doubles are read together into the cache. What is the next access? The next access goes to 10, right? 10 is actually here. So it cause another cache miss because nothing is there. If you assume n is very large, right? So this one actually cause another cache miss here, but then read like a 4, doubles. In the following, in the next iteration, it'll cause another cache miss and to fetch like 4 doubles, and it'll continue. So in other words, there's no special locality. I mean, it keeps, requesting like a new data from new row, and then, every request actually generates cache miss. So in this case, the cache miss rate will be 1, meaning that like 100%. So this one is a very poor access pattern. I mean, in terms of like a locality, this one is a very poor, program. Okay. So remember that. Remember this formula, like a miss rate for like a consecutive like stride 1 access. The miss rate will be the size of the element divided by the block size. And if you actually have this like a column like access, this column access, then cache miss rate will be just 1, right? Because every access generates cache miss. Then now we are ready to compute this cache miss rate for this this code. So let's think about this like a red line here. So what will be the cache miss rate for A? What will be the cache miss rate for B? And what will be the cache miss rate for C? That's what you want to compute. Okay? So here is like an access pattern. So if you see the innermost loop, the A of ik will actually have like this access pattern, right? You actually do nice consecutive row access. And the second B access actually has very poor access pattern, right? Like this, column access, right? Finally, this C is kind of fixed. It actually keep accumulating the same value. So this one is kind of fixed, so it only accesses like 1 point in the array. So everyone get this pattern, right? So A is accessing this like a row-wise, it's accessed row-wise, and this one is accessed column-wise, and this one is simply fixed, right? It doesn't really change in the innermost loop, right? So if you compute, what will be the cache miss rate for this guy? So cache miss rate for this array A will be 0.25, right? Because you have cache miss out of like every 4 accesses. So cache miss rate is 0.25. In case of the second one, the cache miss rate will be 1. And what about C? So to be precise, the cache miss rate will be, it only it's read once, and it keep hits, right? To be precise, this one will be n over 1. Because you actually access n times, but only at the first time, in the first time you have a cache miss. From next time you already have you always have a hit, right? So this one will be actually 1 over n, which is close to 0. We assume to be 0. So this one's misses per inner loop iteration is 0.25 for A, 1.0 for B, and 0 for C. Okay, so everyone get the point here? Okay, so actually can you do better? So let's try to change the order of the loop. Here is ijk, but it doesn't really matter, which order we actually compute, right? You can do like a interchange these two, like a loop order, for example. Now J becomes the outermost loop, and I becomes like the next order, next level, and K is the same, right? So in the previous iteration, we actually we compute this C array in this way. We actually have a C array. We compute the value of Cij in this order, right? In this example, now we compute the same like a C of Cij in this order, right? So that's the only difference. We actually did like interchange of the loop. By the way, this technique is called loop interchange. It's a very well-known, loop optimization technique, the loop interchange. So actually, we did like a loop interchange, and the program semantic is preserved. I mean, the program does exactly the same thing. We only change the order of computation, right? So still, the program output will be the same. So JIK, sorry, actually, JIK. So what will be the cache memory access pattern? So again, for the innermost loop, the access pattern doesn't really change, right? It has the same access pattern. So A is still accessed row-wise, and B is accessed in column-wise, and C is basically fixed. So it doesn't really change the access pattern of the innermost loop. So in this case, again, the misses per inner loop iteration is A is 0.25, B is 1, and C is 0. It doesn't change. Okay. The next trial will be Kij. What about we actually move the K to the outermost loop? Okay. So next iteration will be Kij. So the access pattern will look like this. So now, for a fixed value ik, now you add the sum of this thing. You compute like basically compute like this element, multiply of this element with this thing, and add the value to this row. So actually, this one does exactly the same thing. If you actually take a look at the loop, you first fix a specific like element in the A, and now you access the partial sum for this guy and this guy, because maybe it's actually better explained this way. So now let's say you access like this guy, and you access like this guy, right? Okay, so you actually need to, in order to compute value in C of like a specific like location, let's say this guy and this guy. So now you want to compute the value here, because this one is the row, and this is the same column with this guy, right? So you want to, let's say you want to compute like a specific value, then you need to actually calculate the sum of product for this guy and this guy, right? So you first of all, let's say you fix this point. Then you first compute the value of this one, and this value will contribute to this value, right? And what if you compute the corresponding like element in the next column? So if you actually compute like multiply this value, this box with like this value, and this product will contribute to the next one here, right? So it will contribute the value to like here, next one. What if actually you have one more column here? If you have one more column, the product between this value and this one will contribute the value to the next one here, right? Like here. So that's the reason why you can actually compute the same thing using like in this manner. So you actually fix the value in a specific element in array A, and you basically calculate the product of this scalar value to a vector, And then the vector will contribute the value of like this row in C. And if you repeat, this process for all of this like element in this row, then eventually you get the correct value for this guy. Okay, so that's how we actually compute the same thing in like a different order. So that's basically the code. And if you see here, we actually see very nice pattern here because this one is fixed. So there's like a 0 like cache miss for this guy. And these two, this time actually shows a very nice pattern of like a strided access, right? Like a row-wise access. So because of this, now both of these like matrix or array actually has very low like cache miss rate, like a 0.25 in both cases, right? So this one is definitely a win, right? Because you compare the previous design, in the previous code, the cache miss rate per inner loop iteration was like a 1.25. But in this case, we only have like a 0.5. Cache misses per loop iteration in total. So this one is much better. Likewise, IJK, we can do the same. So for IJK, we do the same, but we only change the order of computation. So, again, B and C actually show very nice, row-wise access pattern, and A is fixed. So now, the cache miss per inner loop iteration doesn't really change in this case. So 0, 0.25, and 0.25. And let's try like one more like combination, like two more actually. JKI pattern, it'll look like this. This one is kind of worse, right? In A and C, we actually have, in both cases, we have like a column-wise like access, and this B is fixed, right? So the cache miss rate per loop iteration will be 1.0, 0.0, and 1.0. So it'll be like over like two misses per loop iteration in total. Likewise, KJI does the same. They actually do the column-wise like access. Okay. So here's a summary. So if you summarize all these like 6 possible combinations for this like a interchange in the loop. If you have like IJK or JKI, then there will be like 2 loads and 0 stores, and misses per iteration will be 1.25, right? Because one actually does row-wise access, the other does like column-wise access. So the average like misses per iteration will be 1.25. And the second one is the best case. Now it's innermost loop, we actually do like 2 loads and 1 store, but the cache miss per iteration will be only like 0.5. Much fewer like cache misses per like a single iteration. Finally, the last case, this one is the worst case. 2 loads and 1 store, and misses per iteration is 2.0, which is the worst case, right? Because we have the fewer cache misses, then actually that's better. We can actually run this code on your machine. Then this one is the actual performance. So matrix multiply performance, and y-axis shows the cycles per inner loop of iteration. So how many cycles to execute like a single like an innermost loop like iteration, and x-axis show the array size. As we increase the array size, in the beginning the performance gap is pretty small because we have like a small array. So maybe it's likely to be fit in one of the like a level in cache level. But as you increase the array size, this performance gap widens. So if you see, this one is kind of order of magnitude slower. Because if you in this y-axis we show in the log scale, right? This is log scale. So this one is like an order of magnitude slower than this one, because this one has execution time, so this one is lower the better. So this one is best case, and this one is second best, and this one is the worst case, right? As expected. So the takeaway here is that by simply interchange, just like as simple as you interchanging the order of the loop, the performance can vary widely. But if you don't understand the notion of the cache, you never understand where this performance difference comes from, right? Because you only in very abstract like a high level, the order of computation doesn't really matter in abstract level, right? But in like a physical, like a real, like a realistic level, it actually has huge impact on the performance, because depending on the caching behavior, your program can perform very well or very poorly, even though the number of operations you do is about the same. Okay, that's the takeaway. And this technique is called, as I said, loop interchange. So loop interchange is a very well-known technique of your program. Okay. If you take the compiler course, I don't know whether who is teaching compiler? The Professor Egger, maybe. Maybe he may touch this like a topic, loop interchange or some optimization techniques in the compiler. May or may not, but this is very important like a topic in like compiler design, because if you design compiler well, then compiler is smart enough to change the order of the loop so that optimize performance and so on. Yes. In this case? Well, it's kind of orthogonal. I mean, this one is like in very like highly threaded GPU like architecture like CUDA. Also, yeah, it's heavily affected by access pattern. But the one thing is that the GPU is designed to tolerate like cache miss latency. So it has a lot of like millions of like threads, so that you always some work to do. So even if you have a cache miss, then if you have cache miss, then you dispatch like another thread to run, so that basically you hide the latency of the cache latency of the cache miss, because you have something else to do. So you can still fully utilize your pipeline even if there's cache miss, right? But in this like CPU, if you actually have a cache miss, then your pipeline have to stall, right? That actually caused the waste. But in case of GPU, like a more heavily like a threaded architecture, the goal is to completely hide this cost of cache miss by dispatching like other threads, available threads, right? That's basically how they optimize performance. But so this like cache optimization technique may not be as relevant in like this GPU like architecture, but it may not be always possible to actually completely hide this cache miss rate, because often like a GPU cache also the cache also have some like a significant impact on performance even on GPU. So yeah, so I mean, so ideally it should not have any impact, but in reality there is actually impact of the cache performance. I mean, this kind of technique can actually affect the performance of the program even on GPU. Okay. Any other questions? 루프 인터체인지 뭐 이런 거는 좀 이해가 되시겠죠? 왜 어떻게 성능이 좋아지는지. 확실히 캐시 미스가 엑세스 패턴에 따라서 줄어드니까 이게 훨씬 성능이 좋아지는 거죠. 실제로 재보면. 그게 워크로드 그 안에 있는 그 실제로 루프 바디가 어떻게 짜여져 있느냐에 따라 다르겠죠. 그러니까 실제로 저런 엑세스 패턴을 따져봐야 되겠죠. 실제로 저게 저런 만약에 패턴을 갖고 있다고 하면은 저런 오더로 하는 게 맞을 거고, 그러니까 실제로 그 내부 루프 바디 안에 있는 그 어레이 또는 이제 어떤 오브젝트에 대한 액세스의 순서가 어떻게 되는지를 보고 그걸 따져봐가지고 이렇게 정해야 되겠죠. Okay. All right. So the next topic, the last topic of this lecture, is about how you can improve the spatial temporal locality. So now we move on to the, improving the temporal locality instead of like a spatial locality. And then we're gonna introduce new technique called blocking. Okay. So blocking is very in a sense is conceptually very simple technique. So the blocking is nothing but you divide like a big chunk of work into like a small pieces, right? And then you improve the spatial locality, temporal locality. Okay, that's the basic idea. So again. Now we actually come back to our like a matrix multiplication example. So this one is our baseline code. So here, we have like a triple nested loop IJK, and C of this one is like the same as C, I, J, right? This is the same thing, but we use like a one-dimensional array. In this case, it's the same thing. So we basically keep accumulating the product of this row and this column, right? And then to compute the value of this thing. You know, is what you already covered, right? It's the same thing, basically. So let's say we actually do some cache miss analysis again. So here's like we make some different assumptions. I mean, so here are a few assumptions we make for this example. First, matrix elements are doubles. It's the same, right? Each element takes 8 bytes. That's the first assumption. And cache block size is 8 doubles. So in other words, cache block size is 64 bytes, right? In this example. So each cache block can hold like 8 doubles. And each double like take 8 bytes. And assume this cache size is much smaller than n. N is like a dimension of the array, right? Let's say again, we compute on very large array, matrix multiply on very large array, and this n is much greater than cache size. So in other words, we never fit this like entire array, entire like matrix in the cache. That's the assumption. So here is if you visualize these iterations, the first iteration will look like this. We actually compute sum of products for first row and first column, and to compute the value 0, 0 here, right? So in order to compute this thing, you have to compute the sum of product for row 0 and column 0. Okay, that actually yields this value. In the second iteration, before doing that, what is the cache miss? What is caching behavior here? So in the first iteration, how many cache misses will be there? So if you remember, this one actually generates cache miss every 8 accesses, right? Because now cache block size is 8. So if you actually, this one is a very nice pattern. So now we're gonna have a cache miss. The number of cache misses will be n over 8, because we're gonna have cache miss in every 8 element access, right? So this one is cache miss from here, and this one is cache miss from here, because this one is pretty bad pattern. So it basically cache miss rate will be 1 here. So this one actually generate like n cache misses. So in total, in the first iteration, the total number of cache misses for this first iteration will be 9n over 8 if you add them up, add the two. We ignored like this one because this one actually generates 1 cache miss only, and then from next iteration it will always hit, right? It's fixed, right? So first iteration, we have like a 9n over 8 misses. So after you execute this program, what will be remaining in the cache? So in the first, for this array, this like red part, this part will be remaining in the cache, right? Because now we accessing this pattern, and then for the last n accesses, we access this part. So now this part will be currently in the cache at the end of the iteration 1, right? But what about this thing? In this case, when you actually have a cache miss here, then it actually read like 8 doubles here. Looks like this. And then now you move on to the next row, and then you again now you read like 8 doubles. And then after you execute them all, now you're gonna have this a red box in the cache. But these are pretty much wasted, right? Because you only use this first element in this box, but the remaining 8 elements will be pretty much wasted. Okay. So what about the second iteration? If you move on to second iteration, it's more or less the same. So if you see here, now you compute the value of 0, 1. Then now we basically sweep row 0 and column 1. Right? Again, at the end, we're going to have a same number of cache misses here, and the total misses will be. So this one will repeat for all the elements we have, because now we have a n by n elements here, and we repeat this process for n by n times, so that the total number of misses will be 9n over 8 times n squared, which will be 9 over 8 times n cubed. That's the total number of misses we have to pay to compute this matrix multiply. Okay, I think I'll actually stop here because I don't think I can finish in like in a few minutes. So time is kind of to finish this part, and we're gonna move on to the